Okay, hello students. So this is your lecture 5 of Laplace transformation and Laplace transform. And in the last lecture, we did your inverse Laplace transform. And after that, we did some of the formulas for inverse Laplace transform for some of the functions. And basically, it was similar that the formulas for some functions that we have done earlier for Laplace transform. So on the basis of that functions, we did the formulas of inverse Laplace transform. So if you remember the formulas of a Laplace transform of a function, then it is going to be very much easy for you to find the inverse Laplace transform. So, and after that we come to the inverse Laplace transform of first shifting property. So before proceeding further, in while finding the inverse Laplace transform of some function, it is very necessary that we can correlate the given fp with the function fx whose Laplace transform is going to be fp. So in some of the cases it can be a very easy function or simple function, but in many of the cases you have to manipulate the function to get the required form where you can correlate the fp with the function the Laplace of with the Laplace of function fx. Similarly, in case of a shifting property, what we look for in the while solving the questions of inverse Laplace transform that are related to a shifting property, we just see that is there any shifting of plus a or minus a in the given fp, so that after removing that plus a or minus a in the fp form, then is it correlating with the Laplace of some function. So in this way we use this inverse Laplace transform of first shifting property. Now I am coming to the inverse of your second property. I'm coming to the inverse Laplace transform of property 2. Property 2 was differentiation, and this is inverse Laplace transform of this property are very important. Let the Laplace fx is equals to fp, then by the property 2 differentiation of your Laplace, it is your minus f dash p. This is, and in general it was more like this one, your minus 1 raised to power n f nth derivative p. So this is your formula for second as your second property, differentiation of Laplace transform, that we have done. Now regarding the inverse, we will be using this only because for higher derivative inverse becomes a bit complicated. So we will be using only this property, that Laplace inverse of f dash p is equals to minus x fx. So from here we got this relation of Laplace inverse, and that is going to be used in our question, that Laplace inverse of f dash p is equals to minus x fx. So here it is a Laplace inverse or inverse Laplace transform of property 2. So now what type of questions that can be solved using this? For example, let us start. Find the Laplace inverse of fp, where fp is ln p minus 1 p plus 1. So this is the Laplace inverse that I have to find. Now this is what he is asking. He is asking for the Laplace inverse of ln p minus 1 p plus 1, and this is will be equals to fx, that we have to find. This is going to be equal to some fx, and the Laplace of fx is going to be equal to some fp. This is here fp, and that is what we have to find, the function fx. Now clearly by looking at fp, if you look at fp, then we can see that we can't correlate this given fp with any of our function. Even if we manipulate it a bit, for an example, for this fp that is given in the form this one, if we manipulate it a bit as we were doing in the previous questions, I will got at most I will reach up to this form. So after this I can't be going anywhere. Reason because I am not able to correlate this formula, this FP with any of my formulas available. So in such type of problems, here the property 2, inverse Laplace transform of property 2 comes into play. What you can do in such things, we differentiate the FP. We differentiate the FP. So if you differentiate the FP, you can see it comes out to be this one. This comes out to be this one. And now here you can see this is the Laplace transform of your f e raised to power x, and this is of e raised to power minus x. So now this will make the things easy for us to work out to find fx. So now in all such cases we take the differentiation of fp. Now f dash p, now we know its Laplace transform. So now we take the Laplace inverse of f dash p. We take the Laplace inverse of f dash p after differentiating fp, and this is your Laplace inverse 1 upon p minus 1 minus 1 upon p plus 1. So when you solve this, this is Laplace inverse p minus 1, Laplace inverse 1 upon p plus 1. So this becomes e raised to power x minus e raised to power minus x. So here this is your equation number 2, and here what you got, Laplace inverse of f dash p. But we need Laplace inverse of fp, that is fx. We need to find fx. Here it is. Can you see that? Here it is. We need this fx, which is equals to Laplace inverse of fp. So now by second shifting property, by the Laplace inverse of property 2, by Laplace transform of property 2 as we did earlier, Laplace of f dash p is always equals to f dash p. Let me write it properly. F dash p is equals to your minus x fx. This is what we have got from the property number inverse Laplace transform of property 2, that Laplace of f dash p is equals to minus x fx. Here it is. This is what we have the result from the inverse Laplace transform of your property 2. So now from 2 and 3, from 2 we derive it from the given fp. Equation 3 we got from the relation of property 2, inverse Laplace of property 2. So from 2 and 3 we got minus x fx is equals to ex minus e raised to power minus x, because both are representing the same thing. This is Laplace inverse that we got after solving fp, taking its derivative and then taking the Laplace inverse, and this we got from the Laplace inverse of your second property. So this implies fx is equals to e raised to power minus x ex upon x. Yes, so this is the solution. This is the solution fx that we are looking for. That is, he was asking you Laplace inverse of fp, that is ln p minus 1 p plus 1, and that is what we were looking for fx, and that in this case has comes out to be this one. So here it is your fx or Laplace inverse of fp in this question. So this is how these questions are important, because otherwise no other manipulation works here except that we take the derivative for such type of questions. Similarly, let us take one more example of this type. We have to find Laplace inverse of cot inverse p. So you have to find this one, Laplace inverse of cot inverse p. So what is asking? He is asking you the Laplace inverse of fp, where fp is your cot inverse p, and you need to find this fx. You need to find this fx. So again, okay, let me now. So here fp is cot inverse p. So clearly you can see, you will not get any idea that which relation it correlates to, which formula it correlates to. So if we take the, however, if we take the derivative, it is minus 1 upon 1 plus p square, or p square plus 1. And now you can see this formula, this 1 upon 1 plus p square, or simply if I write it as 1 upon p square plus 1, this correlates with the Laplace of your sin x. So here, now I take the Laplace inverse of this f dash p, and this comes out to be minus Laplace inverse of 1 upon p square plus 1, and that is minus sin x. So this is equation number 2, that is Laplace inverse of f dash p, that I got from given fp by differentiating it and then taking the Laplace inverse. Also I have Laplace inverse of f dash p. From the inverse Laplace transform of property 2, I have this relation. So from 2 and 3, I got minus x fx is equals to minus sin x. So this implies fx is equals to sin x upon x. So this is my result solution for the given question, that is Laplace inverse of your cot inverse p is equals to sin x upon x. This is the solution for this question. So this is one of the question that we can see make the use of your inverse Laplace transform of property number 2. Now I am taking one more question. If fp is equals to ln 1 minus p square, evaluate Laplace inverse of fp. This is the question. See, you have been given and you need to find the Laplace inverse. So again, since fp here is ln 1 minus 1 upon p square, and you can see that here even in this form you can't do much with this Laplace. So now you can differentiate as we did in our other examples. So when you differentiate it, you get 1 upon 1 minus p square, and in the this is 1 upon 2 upon p cube. Yes, this is what we will get, and then if you sort it out, it will be p square minus 1, p will get cancelled, p square, and then p square minus 1. Yes, so here it is. So here it is. After solving this, you get f dash p in this case. F dash p in this case, you get 2 upon p square minus 1. And now you can solve it. You know how to solve such type of problem. We have done such type of problems earlier. You use partial fraction. It can be, it can be written as p minus 1, p plus 1. This is, and using the partial fraction, that is a upon p plus b upon p minus 1 plus c upon p plus 1, using the partial fraction, it comes out to be f dash p. Even you can do this step of partial fraction while taking the inverse. I am doing it earlier. So this is minus 2 1 by p, minus 2 1 by p, minus 1 by 2 p minus 1, minus 1 by 2 p plus 1. So this is what I will get from the partial fraction of this one, minus 2 1 upon p. Yes, this is. So now I can take the Laplace inverse, or even I could have done this when taking the Laplace inverse. So this is minus 2 Laplace inverse 1 by p 1 by 2 p minus 1, and this is p plus 1. So this is your Laplace inverse 1 by p 1 by 2 Laplace inverse 1 upon p minus 1 Laplace inverse 1 upon p plus 1. So this is how we take the Laplace inverse, and this Laplace inverse, solving it, this is 1, this is e raised to power x, and this is e raised to power minus x. So this is the value, or this implies a Laplace or let me complete it here. This is your equation number 2. This is what we need to find fx. First thing, from fp, take its derivative and then take its Laplace inverse. Also, by the inverse Laplace transform of property 2, f dash p Laplace inverse is equals to minus x fx. From 2 and 3, comparing both sides, we get your minus x fx is equals to minus 2 1 minus 1 by 2 ex plus e raised to power minus x, this one. So fx is equals to your 2, this is your, just hold on, yes it is, this is 2 upon x 1 minus 1 by 2. Is I making any mistake here? Just let me check. So it is fine, minus x, yes, this is going fine, and then ex plus e raised to power minus x, yes this is. So if I just, so this is the solution, yeah, I can write it this as a solution, or otherwise it is your 2 upon x minus e raised to power x. I'm just trying to convert it into some form, 2 upon x, and yes, this one. You can also change it to this form, because this form correlates with the form of your hyperbolic function. I was just trying to, but it is fine. You can just stop it up to here. This is the final answer. So here you got the answer. Fx is equals to your 2 upon x, and then you have your 1 minus 1 by 2 ex plus e minus x. So this is how we can solve these questions. Here in the final, I was just trying to correlate it with the hyperbolic x, and that you can do. You can see here, or if we, let me do not do this one. After this, what we can do, this is 2 upon x, 1 minus, this is your cos hyperbolic x. You know, cos hyperbolic x is ex plus e minus x by 2. So this is what I was looking for. Yes, this is also the form, you can write it. So this is the relation or fx for the given Laplace inverse of fp. So what you were looking for, fx, so here it is your fx, 2 upon x minus your ex plus e minus x upon x is fine. Next is your, so this is how we can solve the questions of your inverse Laplace transform of property 2. Next is your inverse Laplace transform of property 3. Now remember that property 3, what we have, if your Laplace of fx is equals to fp, and then third property says that Laplace of fx upon x, x divided by x, is p to infinity fp dp. So from here the Laplace inverse, p to infinity fp dp is equals to fx upon x. So this is the inverse Laplace transform of property 3. So however, the questions from this property are very less or very few, because questions of this type where you will be getting the Laplace inverse of p to infinity fp are very less, very few or very rare. So we will not be going for the questions of the inverse Laplace transform of this property 3. Only property 1 and property 2, the questions related to the inverse Laplace transform are important, and that we have done. Okay, so after this, I am now coming to your property 4. I am now coming to the property number 4, that is your Laplace transform of derivatives. Remember that what we have done till now, we did Laplace transform formulas of some functions. Then we did 3 properties: first shifting property, Laplace transform of derivative x dot fx, and Laplace transform of integral, that was here. Laplace transform of integral Laplace of fx upon x. These were the three properties. Then we shifted to inverse Laplace transform. We did some of the formulas related to inverse Laplace transform, and then we did inverse of these three properties, out of which the inverse Laplace transform of first two properties, for shifting property and differentiation x dot fx, that were important. Now again coming back to your properties of Laplace transform, and here we will be looking for the Laplace of basically f dash x, f double dash x, these type of Laplace. Now we will be looking in this property 4. So he says let fx be a piecewise continuous function and of exponential order c for all x greater than or equals to 0. Let f dash x be also of exponential order and at least piecewise continuous for all x greater than 0. Then this theorem will tell us how you can find the Laplace transform of derivative. Then the Laplace of f dash x. Till now we have done the Laplace of some functions, Laplace of ex dot fx, x dot fx, and fx upon x. So here is the derivatives. This is equals to your p times Laplace of fx minus the value of function at 0, or p fp minus f0, since Laplace of fx is fp. This is the Laplace of first derivative. The Laplace of second derivative f dash x is p square Laplace of fx minus p f0 minus f dash 0. This is the formula for the Laplace of second derivative. Similarly, Laplace of third derivative is p cube Laplace of fx minus p square f0 minus p f dash 0 minus f double dash 0. And these are the formulas that we can use for finding the Laplace of derivative, and these formulas are very useful while we will be solving the differential equations, because there you can see there we have derivatives first order, second order, so there we will take the Laplace and will use these formulas. In general mostly we will be using up to only second order, because in our syllabus we have done the differential equation only up to second order 2, so we will be using up to this one. But let us write in general what the formula for the nth derivative, Laplace of nth derivative. So this is Pn Laplace of fx plus Pn minus 1 f0 plus Pn, sorry, this is minus, sorry for that, this is minus f dash 0 and so on up to minus p raised to, sorry, this is 0, this is 1, and this is finally fn minus 1 0. Yes, this is. So this is the formula in case you have to find the nth derivative, Laplace of nth derivative. This is Pn Laplace fx, Pn minus 1 dot f0, Pn minus 2 f dash 0, and finally n minus 1 derivative of function at 0. So mostly these type of your questions or formulas are used in while solving the differential equation, but also we can see that sometime if the question is like find the Laplace of f dash x, where fx is equals to e2x sin x upon x, something say has been asked to find the Laplace of the derivative of this function. You have to find the Laplace of derivative of this function. So clearly you can see this function is containing three functions, and that are also in numerator and denominator. So when you will take its derivative, it is going to become a very large function. So taking the Laplace is not a good choice. So it is better that if we use, because its derivative is going to, if we first differentiate it then take the Laplace, it is going to be very difficult. I can just write here the derivative of this function. It is something that comes out of it. Let me write it as such. So this is the Laplace of this function to e2x on x sin x. So this is the derivative of this function. So clearly you can see from here. Or if I sort it out, then it will become e2x dot cos x upon x, and this is, no, it is fine. This is x square and this is x. Yes, this is fine. This is, you can see the derivative of your, you can verify it, the derivative of f. Now taking the Laplace of this is not going to be an easy task. It is going to be very lengthy. So let us use the formula of Laplace, derivative of the Laplace. So derivative of function, and if we take its Laplace by formula, we have p times the Laplace of fx minus f0. This is what. So clearly you can see here, just we need to find the Laplace of fx and then the value of function at 0. These are the only two things that we have to do. So we have to find the Laplace of fx, that is the Laplace of function e2x sin x upon x. This is what we have to find out, first of all, at least. So to find this, you can see here two properties are used. One is fx upon x, and then your first shifting property with e raised to r2x. So let us start. Since Laplace of sin x is equals to 1 upon p square plus 1, so this implies Laplace of sin x upon x. Third property, division by x, is p to infinity 1 upon p square plus 1 dp. So this is tan inverse p to infinity. And solving this, you will get this equals to pi by 2 minus tan inverse p. So finally, Laplace of your, we were looking for e raised to power 2x dot sin x upon x. We were looking for the Laplace of this one, and that is pi by 2 minus tan inverse p minus 2. So this is my Laplace that I need for the formula, and other is the value of function at 0. That is the value of fx at x equals to 0. That is fx is your sin x upon x e raised to power 2x at x equals to 0. So this is, I can write it as e raised to power naught dot sin x at x equals to 0, which is undefined, so I need to take the limit x tending to 0 sin x upon x, and that is 1. So this is 1 dot 1 is equals to 1. So this is the value of f0, function's value at x equals to 0. So this is 3. So put 2 and 3. Put 2 and 3 in 1. You will get 1 is here. This is 1. Here it is. Here we need Laplace of fx that we found, and then value function at 0. So that will give you the Laplace of f dash x without finding its derivative. That in this case was going to be very lengthy. So here, putting 2 and 3 in 1, this gives you Laplace of f dash x, that is Laplace of the derivative of your fx is equals to your p times Laplace of fx, that was pi by 2. Here it is, I have just written here, yes, here it is, pi by 2 minus tan inverse p minus 2 minus the value function at 0, that is 1. That is 1. So this is how we can solve these type of problems where the derivative has been asked and it is complicated. Otherwise, if the derivative is easy, you can just find out the derivative and then apply Laplace transform on it. But if it is complicated, then we can use these formulas always. Otherwise, these formulas of derivatives are used basically in the differential equations while solving that differential equation. So let me now take you to the applications of Laplace to differential equation, to solve differential equation. How we use application of Laplace, because now we are in position that we can now solve the differential equation using Laplace transform. So let us see now how we can solve the differential equation. So first question is, solve the differential equation. Solve the differential equation y double dash plus 2y dash minus 3y is equals to 3 with conditions y0 is equals to 4 and y dash 0 is equals to minus 7 using Laplace transform. So now you can see here. Okay, so clearly we can see here that in this question it is a question of initial value problem, and here in this question this is initial value problem because conditions has been given on a single point. So now to solve this type of problem of differential equation, remember that when we did solve the differential equation in unit 1, there first we solve the homogeneous part, where we solve the general solution or find the general solution of your homogeneous differential equation, and then we find the particular solution of the non-homogeneous differential equation. Then we say that y general plus yp is your general solution of non-homogeneous, and after that we put these conditions, and then we will find the particular solution. In Laplace, the process is not going to be that much lengthy as we did in your unit 1. Here it is easy. You can see here what we do. We take the Laplace of both sides. When the differential equation is given, we take the Laplace of both sides. So this gives you Laplace of y double dash 2y dash minus 3y is equals to Laplace of 3. Now here we separate the terms. This is 2 times Laplace of y dash minus 3 times the Laplace of y is equals to Laplace of 3 is 3 upon p. Now the Laplace of y double dash, basically, so y double dash is, here you can assume y as fx or y equals to yx. You can assume anything like that. Okay, so we use now the formula of the Laplace of a derivative. So it is p square. I am taking y equals to fx. This is minus p times f0 minus f dash 0. You can even take y0, since we have taken y, so let me take it as y. Because since even you can take f, there is not any issue that you can't take here, but let me take y. So this is y0, y dash 0. This is for Laplace of y double dash. Now we come to Laplace of y dash. So this is 2 times p times the Laplace of y or yx minus y0. This is the formula, and then minus 3 times the Laplace of y is equals to 3 upon p. You can always write y as fx or yx or whatever you want to write, in what form you are convenient with. So now we have p square Laplace of y. This is minus y0. From the given question, y0 is 4 and y dash 0 is given to be minus 7. So this is minus 4p and then plus 7 from here. Then from here it is p Laplace of y. y0 is 4 minus 3 times Laplace of y is equals to 3 upon p. So now here you can see that what we do after this, we collect the terms of Laplace y. So collecting the terms of Laplace y, we got p square plus 2p minus 3 Laplace y, and then the other terms which are left, minus 4p, this is, and then you have plus 7 and then minus 8, that is minus 1 is equals to 3 upon p. p. So this is what we have got. So just now let me just arrange it and write it in a way. So now after segregating the terms of Laplace of y, what we do, we, since in the question we has been asked to find the particular solution of this differential equation, that is we need to find the value of y or yx or fx, whatever you want to say, that satisfies this differential equation under these boundary conditions. Okay, so we need y, we need fx, we need yx. So what we are now going to do, we take the terms other than Laplace y other side. We take these to the right hand side, and so that we are left with Laplace y is equals to 3 upon p 4p plus 1 upon p square plus 2p minus 3. This is, so now let me just solve this further so that I can write it in more proper way. This is 4p square plus p plus 3 upon p times p square plus 2p minus 3, and I can write further it in the form of this factor form p minus 1 p plus 3. I am writing it in the factor form, you will know very shortly. So this is Laplace y. I can even stop up to here, but I will be needing, or I will need this type of your formulation for my next step. What is that? Now since I am looking for y, so y will come when I will take the Laplace inverse of this thing. So here is y. Here is now the concept of inverse Laplace transform comes into play while we solve the differential equations. So you can see now that if I have taken Laplace inverse of this thing from here, I have taken the Laplace inverse, I need to change it to the form where I can solve it. So now clearly you can see this is Laplace inverse. I can do the partial fractions here. I can do the partial fractions here, and this comes out to be minus 1 upon p plus 2 upon p minus 1 plus 3 upon p plus 3. So these are the partial fractions. In this case you will get, that is minus Laplace inverse 1 upon p plus 2 times Laplace inverse 1 upon p minus 1 plus 3 times Laplace inverse 1 upon p plus 3. So what you get y or yx, whatever you want to say, or fx is minus, this is 1 Laplace inverse of 1 by p plus 2 times e raised to power x plus 3 times e raised to power minus 3x. So this is the value of y that satisfies the given differential equation under the given initial conditions. So this is the result we got very easily from this using the concept of Laplace transform, which in other cases we have been solving it using the usual techniques. Here we have to use different techniques, and that is in two parts. First solve the homogeneous differential equation, then find the particular solution non-homogeneous. Then you got the general, and after that you put the values of constants, and then you get the general solution. Here we just got the general solution easily. Now this is one of the question related to your initial value problem. Let us solve another question. Solve the differential equation y double dash plus 9y is equals to 1, and your this is given, just hold on, sorry for that. Yes, this is equals to, with conditions, it is given with conditions y0 is equals to 0 and y pi by 2 is equals to 1 using Laplace transform. So he wants to solve this differential equation by using Laplace transform. So clearly you can see it is a boundary value problem, because conditions prescribed are at different points, not a single point. This is a different point at 0 and pi by 2. So this is a boundary value problem. So again you take the Laplace of both sides. We start as usual. Then this is Laplace of y double dash plus 9 times Laplace of y. Laplace of 1 is 1 upon p. So now we use the formula of the Laplace of double derivative. P square, this is your Laplace y minus p y0 minus y dash 0. This is the formula that comes from here. Plus 9 times Laplace of y is equals to 1 upon p. So this implies p square Laplace of y minus p times y0. y0, you can see here, y0 is 0. So you got here 0 minus y dash 0. Since y dash 0, this is the problem or difference in solving boundary value problem. Here you do not have the value at y dash 0. You have been given value at some other point. Okay, so we take y dash 0 as such. We will keep it as such. And then 9 times Laplace of y is equals to 1 upon p. So now let me collect the terms of Laplace of y. So this is p square plus 9 Laplace of y. This is 0. And then you have here minus y dash 0. We keep it as such. You can take y dash 0 equals to constant k or something like that. So this gives you Laplace of y is equals to 1 upon p plus y dash 0. Now since we have to keep Laplace y one side and other terms other side. So here, since we need y, so we now take the Laplace inverse of this right hand side, and in this case it comes out to be Laplace inverse 1 upon p square plus 9 plus y dash 0 as it is constant. So let me write it properly as p square plus 9. Yes, here it is. So I just take the terms separately. So can you see that this Laplace inverse is simply sine 3x by 3. Here it can be solved by taking the partial fractions. So 1 upon p square plus 9 can be written as a upon p plus cp plus d upon p square plus 9. Otherwise it is very easy. Even if you are not doing, you can just write these terms and see how we can make or multiply somewhere or elsewhere. So this is minus p square plus 9. Here should be p, and this is 1 by 9. So p square plus 9 minus p square 1 by 9 cancel. So you can also do this because these are simple ones. So we need not to do even these type of calculations or partial fraction for this. But when you will have practice, at least for such type of thing, you can do it directly like this one. Just write these two and then see what we can multiply here and divide here to make this term. So now this is your first term, and other is already you have got y dash 0. This is sine 3x upon 3 because this is p square plus 9. Laplace of sine 3x is your 3 upon p square plus 9. So clearly you can see Laplace inverse of 1 upon p square plus 9 is sine 3x by 3. So now 1 by 9 from here, Laplace inverse of 1 by p, 1. This is cos 3x. This is cos 3x plus y dash 0 sine 3x by 3. Now we have reached the point where usually our question ends, but in this case although we have got the most of things, but still one unknown thing is still there, that is y dash 0. That is y dash 0. So how we can get that? We now use the other condition that was given, that y at pi by 2 is given to be 1. So this is the condition other that we haven't used in the question. So when you put y pi by 2, this is 1 by 9, 1 minus cos 3 pi by 2 plus y dash 0 sine 3 pi by 2 upon 3. So this is equals to 1 as given here. This is 1 by 9. This is 0. Y dash 0 sine, this is your minus 1 and upon 3. So solving this, you will see, you will get y dash 0 is equals to minus 8 by 3. So here the thing that This is the difference in your initial value and boundary value problem. The y dash usually that is left in the equation is found by the other condition that has not been used. So put it in 2, that is here. We have already got the solution, just only problem was this y dash naught. So we have got this minus the value of this y dash naught. So putting here, we get the particular solution as 1 by 9, 1 minus cos 3x, and this is minus 8 by 9 sine 3x. So this is the solution. This is 1 by 9, 1 minus cos 3x, and yes, here it is, minus 8 by 9. So this is the required particular solution of a given differential equation. That was a boundary value problem that satisfies the given differential equation along with those boundary conditions. So this is the applications of Laplace transform, and you can see how easily we can solve this differential equation using the concept of Laplace transform. And with this, I am closing this lecture. Thank you. Thanks a lot.